Word up. Nationwide hated. Nickel plate.
Sequel or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
Okay, let's get started. It's a huge pleasure to have Kaisen Kang from StarRocks tell us about who Kaisen is a team lead on the query engine team, and he's gonna tell us about the StarRocks query optimizer. Andy is on the phone. I think he'll join in and out. So apologies that he couldn't be here, but Kaisen, we are super excited that you are taking the time to talk to the database group. And of course, thank you to everyone joining us over Zoom. We will post this on the YouTube channel that Andy had set up after the call. But Kaisen, if you think you say something that you wanted to delete, let us know. So feel free to speak your mind in this call. And really appreciate you. I know you're in Singapore, so it's really late. Thanks for bearing with us. And the floor is yours.
Okay, thank you. Good afternoon, everyone. My name is Kaisen Kang. Thank you very much, Andy, for inviting me to speak here. Today, I'm very pleased to share insights into StarRocks Query Optimizer. In the past 10 years, I have been engaged in OLAP database-related work, with active contributions to Apache Kitten, Apache Doris, and StarRocks open source communities. Over the last 5 years, my team and I have built the StarRocks vectorized execution engine and StarRocks Query Optimizer from scratch, making StarRocks an extremely fast query engine. Today, I will share StarRocks Query Optimizer from 4 parts. First, we will begin with the overview of StarRocks and StarRocks Query Optimizer. Second, I will introduce the 3 representative optimizations of StarRocks Query Optimizer. Third, I will introduce the common challenges of CPU and StarRocks solutions. Finally, I will share some insights and lessons learned from our experience in building the StarRocks Query Optimizer. To begin, allow me to provide a concise overview of StarRocks development journey. Over the past 5 years, we have launched 3 major versions. StarRocks version 1 built an extremely fast OLAP database, leveraging a vectorized execution engine and cost-based optimizer. StarRocks version 2 evolved into a high-performance unified OLAP database, introduced features like the primary key model, data lake analytics, and comprehensive query optimizations. StarRocks version 3 built an open lakehouse architecture driven by storage and compute separation, multi-views, and advanced data lake analytics. This diagram illustrates the overall architecture of StarRocks, which includes 2 components, front-end and compute node. Front-end is responsible for managing in-memory metadata, query optimization, and query schedule. It is implemented in Java. Compute node handles data catch from the data lake and query execution. It is implemented in C++. This diagram shows the overall architecture of StarRocks Optimizer. The overall framework of StarRocks Optimizer is implemented based on the Cascades and Columbia papers. The memo data structure, search framework, rule framework, and property enforce of StarRocks Optimizer are consistent with the Cascades. This diagram shows a more detailed optimization of process of StarRocks Optimizer and also reflects several differences with the Cascades framework. StarRocks Optimizer uses multi-phase optimization strategy, including logical rewrite, cost-based optimization, physical rewrite, and feedback tuning. Specifically, the logical rewrite phase performs tree-to-tree transformations, apply a sort of common rewrite rules, such as subquery rewrite and common table expression inline. The cost-based optimization phase leverages the Cascades memo structure and includes important cost-based rules, include join rewarding, join distribution strategy selection, and aggregation distribution strategy selection, and multi-view rewrite. The output of the cost-based optimization phase is a distributed physical tree. Subsequently, The physical rewrite phase executes a few physical rewrites that do not affect the cost, including global dictionary rewrite, which will be discussed in detail today, and common expression reuse. The last feedback tuning is a new feature implemented in 2024, which will be shared later. Feedback tuning adjusts the execution plan based on the feedback information and runtime. Now, we have a general understanding of StarRocks optimizer. Let's take a deep look at it. I will focus on two key areas. First, three representative optimizations, and second, StarRocks approaches to addressing common cost estimation challenges. The three representative optimizations we will apply are multi-left join collocate, global dictionary optimization, and partition multi-view unit rewrite. The three solutions to cost estimation problem include query feedback, adaptive execution, and circle plan management. Let's first look at the multi-left join collocate. In distributed database, the distributed execution strategy of join include shuffle join, broadcast join, replication join, and collocate join. Shuffle join involves redistributing the data of both tables to the same execution node based on the join key, which needs network data transmission. And the shuffle join involves redistributing the data of both tables to the same execution node based on the join key, which needs network data transmission. Collocate join, in contrast, leveraging the pool distributed data where both tables are already collocated on the same node according to the join key, enabling a local join execution without network data transmission. In StarRocks, the distribution strategy for join operation is determined by the distribution property enforcer. On the left, we can see an example of a shuffle join enforcer. The join operator requires the distribution properties of hash A column and hash B column. Since T1 and T2 are normal tables that do not inherently satisfy these distribution requirements, shuffle exchange operators are enforced on the scan T1 and scan T2 operators. On the right, we have an example of a collocate join enforcer. The join operator still requires the distribution property hash A column and hash B column. However, in this case, T1 and T2 are collocated tables distributed according to the hash A column and hash B column. Consequently, the required distribution property are already satisfied, eliminating the need for shuffle exchange operators and enabling direct local join execution. Now, let's examine the multi-inner join collocations.
Question, do you have a notion of a broadcast join, or is that covered by what you have here?
Broadcast join is more easier. This case we are only compare the shuffle join and the collocated join.
Got it. Okay, but the optimizer will consider a broadcast join in that last phase where it looks like you were thinking about the impact of distributed execution, right?
Yes, of course. We will both in StarRocks optimizer we will all consider the shuffle join, broadcast join, and collocated join.
Okay, great. Thank you.
Thank you. Now let's examine the multi-inner join collocation. As illustrated in the diagram, after the T1, T2, and T3 are collocated based on their respective bucket columns, the collocated process for both two-table and multi-table joins become identical, enabling direct local join execution. This is because after the inner join of the T1 and T2, the physical distribution of inner join result is exactly as the same as the T1 or T2. Before introducing a multi-left join collocate, let's first confirm the difference between the left join and the inner join. We all know that the left join preserves all rows from the left table, and for any rows in the left table, then the line corresponding match in the right table. The corresponding columns in the right table are populated with non-values. As shown in the diagram, the second row in the column C1 of the table T2 is assigned a non-value. Consequently, when multi-table left join distribution property enforce is applied, The C1 column on T2 table after the left join operations differs from the C1 column of original T2 table. The required distribution properties are unable to satisfy, which prevents the execution of a collective join. However, let's analyze it further to see if this left join circle really cannot do collective join. First, we could observe the table on the left, which shows the real result of the left join circle. Next, examine the diagram on the right and consider whether the non-value in the C1 column on T2 would yield a different result between the collective join and the shuffle join. We understand that a non-value compared to any value will always evaluate none. Consequently, regardless of the whole non-value in C1 column on T2 and their corresponding C1 column on T3, values are distributed. Whether they reside on same execution node or not, the join result remains none. Therefore, we can infer that the distribution of non-values does not expand the feasibility of collective join between the T2 and T3. Given the non-values in T2 and T3 satisfy the collective distribution requirements, T2 and T3 can indeed be collectively joined. So, in order to make a distribution property enforce support this case, StarRocks introduced the non-relax and non-strict mode in the distribution property. For the non-rejecting join unpredict, StarRocks will generate the non-relax mode and ignore non-value when comparing properties. Conversely, for non-safe equal joins, StarRocks will generate a non-strict mode, ensuring the non-value are considered when comparing properties. With the implementation of non-relaxed and non-strict mode, we can now examine the multi-left join enforcement process. Since the parent requires the Hashi C1 column T2 of T2 with the non-relaxed mode, and the child also produces the Hashi C1 column T2 with non-relaxed mode. So it satisfies the distribution property requirement of the parent node during enforcement, thereby enabling the collective join.
Kaisen, there's a question. Maybe I'll ask before you jump to the other part. Andre asks, how do you manage the explosion in the combinations you have to cover because of a shuffle join? So if you have 100 data nodes, you'll have to consider like this 100 by 100 combination for that second stage. So do you have a strategy for dealing with that?
Yes, and for if the join node is very a lot, and in the join reorder process, and we will only to take the such as the top 10 or the top 20 the join combination, and then combine the distributed property enforce. So with this way we could control the join combination number.
And how do you pick the top 10 or 20 in that? Is that like heuristic driven, or are there some other ways for you to pick that?
We use some of the statistics, and we will estimation the clinality of the join result, and in the join reorder rules.
Got it. Okay, thank you.
Thank you. Next, let's turn our attention to the low-clinality global dictionary organization. To begin, let's define the dictionary organization. Dictionary organization is operations on encoding data. For dictionary encoding data, computations are performed directly based on the encoding data without decoding first. As illustrated in the diagram, the platform column is directly encoding the storage layer, so the field operation of the platform will be directly based on the encoding integer data. The platform equal ls will become the 1 equals 0 or 1 equal 1, and integer compression will be much faster than string compression. Dictionary optimization in storage layer is supported by StarRocks version 1, but only supports the field operations, and the optimization scenarios are very limited. So in StarRocks version 2, we support the global locality dictionary optimization. A keyword here is locality, because if the cardinality is high, the cost of maintaining the global dictionary in a distributed system will be very high. Therefore, our current cardinality limit is relatively low. The default configuration is 256. For many dimension table string columns, we think the 256 is enough. And importantly, StarRocks Global Dictionary implement is entirely transparent to users. Users do not need to care about which column and when and how to build the global dictionary. Leveraging the global dictionary, our dictionary organizations extend to support the broader range of operations and functions, including the scan, build, aggregation, sort, join, and string functions. This diagram illustrates an example of a global dictionary organization applied to the global operation. StarRocks maintain a global dictionary for city and platform columns. During the global operation, StarRocks transforms the string-based global into an integer-based global. In this example, you could see the global key from the Andrew Beijing or Andrew Shanghai becomes the 11 or 12.
So are these global dictionaries global just to a column, or they can be shared across different columns too?
Which is for one column we will have one global dictionary.
Okay. But can you also share that global dictionary across multiple columns that might just have cities but may not exactly be called cities, or it just sounds like it's specific only to a specific column?
You could see from this diagram, we have for the platform column, we have a global dictionary, and for the city column, we have a global dictionary.
Okay, thank you.
Thank you. Yes, we could see this example, and StarRocks maintain a global dictionary for the city and platform column. And during the global operation, StarRocks will transform the string-based global into an integer-based global, which would result in a significant performance gains and for the operations such as scan, hash, echo, and memory copy. And this optimization typically yield an overall query performance improved of 3 times. Given the today's session focused on optimizer, let's focus on how StarRocks use the global dictionary to rewrite the plan. This diagram provides a high-level schematic representation of a global dictionary plan rewriting process. Firstly, the rewrite operations take place during the physical rewrite phase. We transform locality string column into integer column. For successful rewriting, 2 conditions must be satisfied. First, the string column in the plan is a locality column, and the FE memory has a global dictionary corresponding to the string column. And upon successful rewriting, the global dictionary along with the modified execution plan are transmitted to the query executor. This diagram provides a detailed repetition of the global dictionary plan rewrite process. Currently, StarRocks supports optimizations for string and array string data types. The end-to-end rewriting process operates on physical execution tree, employing a bottom-up traversal approach. If a string column could do a locality optimization, it is rewriting as an integer column, and all string and aggregate function referencing this column are modifying accordingly. Conversely, if a locality optimization couldn't be done on a particular operator, a decode operator is inserted. And this decode operator, the integers column is transformed back into a string column. Now, let's move union and rewrite part. And StarRocks have support for synchronized multi-view since the version 1, and invalid MV to a codfish in the version 2. And we have support the for new asynchronous MVs and expanded from single-table MV capabilities to multi-table MV support. And emulating the significant optimization enhancement in the automatic query writing. And today's presentation will focus on the MV query write aspect. StarRocks currently supports the automatic material rewrite across the wide range of scenarios, including the aggregation rewrite, join rewrite, union rewrite, nested MV rewrite, and test-based rewrite for the complex circle queries, and view-based rewrite for the circle with view. Today, we will focus on the union rewrite. First, let's think about why we need the auto MV union rewrite. The first case is the query on data lake scenario. StarRocks can directly query data lake table formats. If you accept to achieve sub-second performance, you can use MV to speed up queries on the data lake. But most users only focus on query performance in recent period. So they only need to build MV for the data in the last week or the last month. However, users may occasionally query data in the last 2 weeks or the last 2 months. And this time, the optimizer needs to automatically rewrite the query and union the recent MV data with the historical data lake data. The second case is a real-time scenario. We expect to use MV to achieve millisecond level queries at tens of thousands QPS, but the refresh MV has a delay and cannot guarantee that the list data is consistent with the base table. To ensure user receive the accurate and up-to-date query result, we need to union the MV data with the latest data in the base table. Let's first consider the case where all partitions of MV are refreshed. As illustrated in the diagram, the query and the material views both involve the simple inner joins, but with different predicted ranges. Since the MV result set is a subset of the query result set, we must generate the conversation predict to append to the original query, and subsequently perform a union operation. In this example, the conversation predicts are the cascade large 10 and the cascade less than 20. The predict, classify, and conversation logic implementing StarRocks align with the approach described in Microsoft research paper, optimizing queries using material view, a practical, scalable solution. Next, let's consider the case of a partial MV partition refreshed. If both MV and query are simple group by count queries, MV and base table both have 4 partitions, which of the P1 and P2 partition of MV have been refreshed, but P3 and P4 have not been refreshed. The rewrite of this aggregate query will become the union of MV query and the query of original table. The left child of union is the scheduled of the MV, and the right child of union is the plan of original query. The only difference of the original query is that the partition of the scan becomes the partition of the MV that not being refreshed. In this example, which are the P3 and P4 partition. Finally, let's consider the case of the partition MV with predict rewrite. Let's illustrate with an example. Imagine our base table is partitioned into the February 1st and February 2nd. The material view for the partition February 1st is up-to-date and refreshed, while MV for the February 2nd is still and to refresh. The MV is defined as the select star from T, where the A large 20, and our query is the select star from T, where A large 10. In the first step, we begin by assuming all MV partitions are refreshed. Ignore the MV partition state for now. In this phase, we apply the rewriting techniques outlined in the Microsoft paper. And then in the second step, we consider the MV refreshness and partition refresh state, and the partition compensation predict to MV scan in the first step. Finally, we merge the result of the first 2 steps to get the final result, and you can in the final plan, which has the two union. Now, let's move the third part, the CPU challenges and StarRocks solution. Over the past several years, we have continued to encounter many challenges in the cost estimation, which I think are also the challenges that all CPU optimizers will encounter. For example, no statistical information and inaccurate collection of the sampling statistics information and inaccurate estimation of the sampling statistics information. And even if the statistical information is accurate, the cost estimation will be wrong because the basic assumption of the independency of the irregularities are not valid, or the errors of the multi-level join are applied layer by layer. There are also cognitive skill problems in the production environment. There are also problems with production environment plan jitters exposed by some users in the past year, which will cause some small queries to become large queries and leading to the production environment accidents. Today, I will mainly introduce the query feedback, adaptive execution, and circle plan management. Before diving into these advanced features, let's briefly review the basics of StarRocks statistics. First, StarRocks single column statistics include the basic count, max, mean, distinct, and also support histogram. StarRocks statistics support the manual and automatic collection, and each collection supports the both for and sampling methods. To minimize the query planning latency, statistics are cached in the front-end memory, allowing the optimizer to efficiently retrieve the column statistics directly from memory. And by default, StarRocks automatic collection employing a strategy of performing a for analyze on smaller tables and sample analyze on larger tables. The difficulty of collecting statistics information is to make a trade-off between the resource consumption and accuracy, and which also avoiding the statistics information collection task from affecting the normal important and query. StarRocks optimizes the accuracy and performance of statistics collection in the following four aspects. The first point is metascan. StarRocks uses metascan to optimize the statistics of count, mean, and max, reduce the resource consumption. And the second point is table sampling. When sampling, it will import the accuracy as much as possible while only scanning a small amount of data. StarRocks will reduce the cost of statistics collection by reduce both of number collections and columns. The third point is the predict column. Table sample and predict column will be introduced soon. The last point is to reduce the impact of statistics collection on normal queries and ingestions. StarRocks currently support executing statistics tasks in a separate warehouse, and which ensures the statistics collection jobs will not affect the query and ingestions. Let's introduce the table example. StarRocks table sampling will follow the actual physical distribution of table data. As you can see from the diagram, StarRocks table will first be partitioned by the range, list, or expression, and then followed by the hash or random bucketing. And each template will divide into the multi-segments according to the size, and each column or page will divide into multi-page according to the 64 KB each. When StarRocks performing sample statistics, it will read data from some tablets and some segments. As for which pages of data to read in each segment, StarRocks will use different sample algorithm according to the different data distribution characteristics. StarRocks will first sort the page according to the max mean values of each page's map. If the data is found to be highly clustered, the history-based uniform sampling algorithm will be used. If the data is found to be less clustered, the Bologna sampling algorithm will be used. The core idea of predict columns mentioned before is very simple. We believe that when a table has thousands or hundreds or thousands of columns, only the statistics information of few key columns will affect the quality of final plan. In OLAP analytics, these columns are generally dimension columns, such as the fuse column, group by column, distinct column, and join on column. So we only need two characteristics for the predict columns. Now let's move the query feedback part. As mentioned earlier, query feedback is used to solve the problem of inaccurate cost estimation caused by any reason. The core idea is to use the real runtime information to correct the bad query plan, so that the optimizer can generate a better plan next time. StarRocks query feedback does not update the statistical information, but record a bad plan tuning guide for each type of query. As shown in the diagram, query feedback has two core models: plan tuning analyzer and circle tuning advisor. Plan tuning analyzer checks whether there is a clear bad plan based on the real runtime information and execution plan of the query. If a clear bad plan is detected, it will be recorded. When the optimizer generates the final plan, if it found that the corresponding tuning guide is recorded in the circle tuning advisor, it will apply the bad plan in the tuning guide. Currently, the first version of query feedback can mainly optimize three types of keys. The first is optimize the left and the right order of join. The second is optimize the distributed execution mode of join. Example, the broadcast join to shuffle join or the shuffle join to broadcast join. And the third is for the case where first phase aggregation work well, disable streaming aggregation and aggregate more data in the first phase. And we will introduce the streaming aggregation soon. This is a use case of query feedback, which corrects the incorrect order of the left and right tables. On the left query profile, there is a large table with 50 billion rows on the right, and a small table with 1,114 rows on the left. When the large table is used to build a hash table, the performance will be very poor. And in StarRocks, we should use the small table to build the hash table. And after applying the feedback tuning, the join reorder becomes right. And at the same time, you can also find in the right query profile, there are only the 1,119 rows of data in the left table. This is because the runtime filter is ineffective, and the data in the left is filtered out. And I will introduce the runtime filter soon. And you can see that the query time of the two different plans is an order of magnitude different. This is a second use case of query feedback, adjusting the incorrect shuffle join to broadcast join. As illustrated in the diagram, the left and right children of the left join are both exchanged, which indicates this is a shuffle join. But we found the data in the left table is only has the 11,998 rows, and the broadcast join is obviously a better execution strategy. And after applying feedback tuning, shuffle join is adjusted to broadcast join, and the runtime filter is also effective. And at the same time, we could also see that the query time of the two different plans is also orders of magnitude different. Next, let's learn about the adaptive execution. Let's first learn about the adaptive streaming and aggregation. For simple group by queries, select count star from table group by ID. If it is a non-collocated table, StarRocks will generate two distributed execution plans. And the first plan is a distributed two-phase execution. As illustrated in the diagram, in the first phase, StarRocks will first aggregate the data using a hash table according to the ID column, and then send the data with the same ID to the same node through the hash shuffle. In the second phase, a final hash aggregation will be performed, and then result will be returned to the client. Why do we need to perform a local aggregation in the first phase? Because we expect to reduce the amount of data transmitted by the shuffle network through the first aggregation. Obviously, the assumption here is that the first local aggregation will have a good aggregation effect, such as the input row is 1 million rows, and after hash aggregation, the hash table size is only 1,000. So The two-phase aggregation plan is generally suitable for the median and low cardinality group by columns. The second distributed extreme plan of StarRocks group by is one-phase aggregation. That is, shuffle the data directly after scanning the data, and only do the final aggregation. Obviously, one-phase aggregation is suitable the case where local aggregation has no aggregation effect, such as the input row is 1 million rows, and after the hash aggregation, the hash table size is still 1 million. So the one-phase aggregation is suitable for the high cardinality group by columns. And in theory, as long as the optimizer can accurately estimate the cardinality of group by, we can directly select the correct one or two-phase plan. However, we all know for multi-column group by cardinality estimation, this is very challenging because of multi-column group by are generally not independent and correlated. Therefore, in StarRocks, we did not solve this problem in the optimizer itself, but hope to solve this problem adaptively at the execution layer. The StarRocks optimizer will generate a distributed two-phase aggregation plan by default. Then it will adaptively adjust the aggregation strategy according to the actual aggregation effect obtained during the execution. As illustrated in the diagram, the principle of the StarRocks adaptive aggregation is as follows. In local aggregation, for each batch of data, assuming the 1 million rows, StarRocks will first use a hash table to aggregate the data. When it is found there is no aggregation effect, it will no longer add the data into the hash table, but directly shuffle to avoid the meaningless hash aggregation. And this is the core idea of adaptive execution. And the specific algorithm is really complex. And in the past 5 years, we hope we have optimized several versions, and we will not go into it deep today. But if you are interested, we can discuss on offline. Next, let's look at another case of adaptive execution, adaptive runtime selection, runtime field selection. First, let's quickly understand what runtime field is. In some papers, runtime field is also called sideways information passing. The figure is a simple schematic diagram of join runtime field. After scanning the read table data, StarRocks will build a runtime field for the read table data and push it down to the left table. Runtime field can fill the data in the left table before joining, which could reduce the I/O, network, and CPU resource. For the complex circle, runtime field will have dozens of time performance improvement. In the past 5 years, StarRocks have been continually improve runtime field. Listed on the left are some features of StarRocks runtime field. However, runtime filters may have negative optimizations. When there are many join tables and many join conditions, many runtime fields may be pushed down to same scan node, which will lead to the following issues. First, some runtime fields are ineffective, which will waste CPU resource. Second, filters with low selectivity are used last, and some filters with high selectivity are applied first, which will also waste CPU resource. And some databases may rely on the optimizer to estimate the selectivity of the runtime field, but StarRocks choose to use adaptive execution to solve this problem. As illustrated in the diagram, StarRocks computes the actual selectivity of each runtime field after a certain number of rows of data, and then adaptively adjust the application of the runtime field. Here are some basic adjustment principles. First, only select fields with a low selectivity. Second, only select the 3 fields and most. Third, if the selectivity of the field is particularly low, and only keep 1 field. Let's move the last part, circle plan management. Finally, let's introduce the circle plan management. We are currently developing this feature and will release the first version soon. We decided to develop this feature because over the past year or so, some users online, small queries become larger queries due to plan jitter, which lead to the production accidents. Our aim with the circle plan management is to address the two challenges. First, preventing the performance regression after upgrades. We want to guarantee the query performance remains stable and predictable, eliminating the significant slowdowns caused by plan changes following system upgrade. Second, maintain the stable performance for critical online workloads. We seek to ensure the query plan for essential continuing running business applications remain consistently efficient, avoiding performance degradation over time. Circle plan management is divided into two parts in principle. First, how to generate and save the baseline plan, and second, how to apply the baseline plan. And how to generate a baseline plan is divided into three steps. First, parameterizations of constant. Replace the circle constant with the specific SPM functions, and the SPM is the short of the circle plan management, and which is a placeholder for the constant value. Second, and generate the plan, and we will generate a distributed physical plan based on the parameterized plan. And you could see which is a shuffle join and bucket shuffle join. The bucket shuffle join means only shuffle one table data to another table. Another table data remains unchanged. And the third is the generate baseline circle. And we will convert the physical plan into the circle with hint. In StarRocks, if a join circle with, has a join hint, and StarRocks won't do a join order. So the shuffle and the bucket hint almost determine the two key points of this circle plan: join order and join distribution execution strategy. So why StarRocks save the bound circle with the hint, not the physical plan? Which because first, if we storage the physical plan, and the storage may be very large, and if we only save the circle with the hint, which could save the storage space. And the second is circle with hint is easy to validate. And using base plan is divided into 4 steps. First is also the parameterization of constants, and the second is the guess the baseline circle, and we will compute the digest of the parameter circle and found the corresponding baseline circle in the plan storage according to the digest. And the third is replace the SPM functions in the baseline circle with the constant of the inflow circle. And the fourth is we will process the circle with hint according to the normal query process. Okay, let's move the last part and some lessons from the StarRocks optimizer. And the first is I think the errors in optimizer and cost estimation are avoidable, and the executor need to be able to autonomous decision and provide timely feedback. So I think the adaptive execution and query feedback are necessary for cost-based optimizer. And the second is in engineer. The optimizer test system is important as the optimizer itself. The optimizer requires the character testing, performance testing, and plan quality testing, and so on. I believe that our open source database ecosystem would benefit from the open source testing system for optimizer and the query engine, along with the public available test dataset. And this could specifically accelerate the transition of database optimizer from the demo to the maturity. And the third is I think the non and number is interesting and annoying. And for performance, and we need to special handle the non and the number. We could see it from the collocated join case, and especially if your query engine is a vectorized query engine, and you also need to do many special optimizations for the number columns. And for correctness, and we need to take care of the non and number in the optimize and execute. And to be honest, in the past few years, because we write the execute and optimize from scratch, and we met many bugs about the non and number. Sorry.
That's fantastic.
Sorry.
I'm sure everyone is clapping too. So that's great. Wonderful.
Sorry.
Open it up for questions. If anyone has a question, just unmute yourself. Andre, go for it.
Yeah, I have lots of questions, honestly, but the main one, what is the magic of identifying bad plan? How do you understand that your query was planned badly?
Kaisen,
What is the criteria?
Okay. I get it. So, so question is in the query feedback, how we identify the query is a band plan, right?
Yes, because execution time may be different, maybe a minute, maybe 1 second. It doesn't matter. Your plan may be good, maybe bad. How you identify it?
This is because in the query feedback we have the we know the query plan, and we know the real runtime information, such as the input rules and output rules for the each operator, and we also know in the real selectivities for some future. For in this case, the left is the circle plan, and we know it. And we also know it, also need the left child and the right child the output rules. So we based on this information, we could know it then the shuffle join plan is wrong, and we should use the broadcast join for this circle.
But it's not automatic. You don't do it automatically. Yes? So it's manual work.
Which is automatically.
Okay.
Because after the circle execution finished, and in the front end the query optimizer, and will both know the real execution plan and some of the real runtime information, such as the input rules and output rules for each operator. And in this, so we could check whether this plan is bad or good. Because in this case, if the left child is only has the 1,000 rows, obviously this case the broadcast join is obviously a bad plan. So if only once we know some real runtime information, we could know whether this is a bad plan.
The question, actually, I have a follow-up comment here. So this kind of thing is more like a tuning recommendation, right? So after you execute the query once or twice, then you have the statistics, you improve it, right? So next time you run the same query again, then you can make it more optimal. Is that right?
Yes, we only need to improve in the next time. In the first time, after this query is finished, and we will know this is the plan is banned, and in the next time, and we will try applying the to the guard and to improve the query plan.
Okay, thank you.
But how you identify the same query? Constants may be different, and they may need different plan. The different plan will be optimal for this set of constants. Do you understand?
In the first version, and the circle must be same, but in student, and we will support the parameterization, and we will support the different constant values and for the circle. Both because in the query feedback feature and the circle plan manager feature, we both need to support the different constant values, and we will support it soon.
Okay. May I ask one more question?
Yes, please go for it.
Yeah. Off the top of my head, I can remember some constructions like group by having, for example, which mesh all our statistics, column statistics at all. So and causes big join trees full of nested loops. It's quite common in my practice. How you address this problem? How you deal with such stuff which you can't cover by statistics?
Could you repeat your question again? Sorry.
Yeah, group by, especially with having construction, it broke your statistics on a column because you have only distinct histogram, what else, MCV, but having it's something totally different, and you don't know anything about distribution of data after having. How you solve, what are you doing in the upper query tree? How you decide which type
Andre,
of join to use?
if I were to rephrase your question, you're saying for
Yeah,
aggregation,
please.
you don't know what the output number of group buys is. So how do you adjust or how do you figure out what's the right plan for the aggregation? Is that the question?
Yes, exactly.
Okay. Yeah, Kaisen, you explained that two-level, you start with a two-level aggregation and then you adapt to it. So maybe you can explain that in more detail.
Oh, okay, I get it. Because by the default we prefer the two-phase aggregation, and in the runtime or real execution, and we will for the each batch of data such as 1 million rows, and we will check whether there has a great aggregation effect, such as if we found input rows is 1 million rows, if the hash table size is 1,000, and we think this has a good aggregation effect, and we will still use a hash table. But if we found the hash table size is still 1 million, which means the hash aggregation is meaningless, and so we don't use the hash table. And so I will directly shuffle the data. And in this phase, we will change the for the original we will change the original table format to the serialized format for the aggregation, such as for the sum. Sum, if the input column is int, is an integer, and the data type for the sum integer is a big int. So if we decided to shuffle it, and we will in this step we will also change the input column from the integer column to the big int column, which will be which I will change the data type. So in the final aggregation we could directly handle it.
And Kaishan, seems like for this adaptiveness, you do it on the fly while the query is running, correct? As opposed to the join stuff, which happened, the adaptation happened across queries, not while the query was running. Is that correct? That this is happening on the fly while the query is running.
Yes, and this is only for the group by queries, and not adapted for the join.
Yep. Okay. Great. I have a question. Can you talk a little bit about the types of applications that are typically running on these on StarRocks? Do you see them as having, 10, 20 joins, or are they typically star schema and small number of joins? What's the toughest application that you see that really stresses the optimizer for you?
If we found the join node has many, and we will do very simple join reorder for it, and we should and we will use the gradient join reorder for it, and we don't do a lot of optimization for many join node reorder.
Okay, great. And I know, of course, StarRocks from your website seems like it's used in a large number of applications. Can you talk a little bit about some of your your biggest applications? Like how big is the database? Are you going against petabytes of data, or what does that scale look like, and how many nodes, if you can share that information?
Oh, yes, as far as I know, for the largest users, and the data size should be in the PB size. And for the node, as far as I know, in the one cluster, we should have the hundreds of nodes.
Okay, that's great. Wonderful. Any other questions?
Yeah, I have one more question. Pardon. You said you may save the best query plan. What about specific nodes? For example, you may choose merge join or hash join and decide it is better. May you save this local decision and use it in this query plan or maybe in different query plan? May you identify somehow query node? Specific join, for example, with specific number of filters.
For the join, StarRocks currently only support the Hashi join, and we don't reuse the plan for the join, and the join plan is generated by the optimizer, and we won't reuse it.